Every time you ask an AI model a question, render a high-resolution video, or refresh a feed, you're taxing a global data infrastructure that is perpetually starving for more processing power. In 1965, an engineer named Gordon Moore made an observation that would dictate the trajectory of the modern economy. He noticed that the number of transistors you could fit onto a microchip seemed to double roughly every 2 years. Keeping that pace alive required a brutal physical trade-off. To continue shrinking components inside consumer electronics down to microscopic dimensions, the industrial hardware required to manufacture them had to grow in the opposite direction. Moore's law is not physics. It does not happen naturally. Right now, it's on life support, maintained entirely by the engineering inside a single machine. This is the ASML TwinScan EXE5000. It is a high-NA extreme ultraviolet lithography system, and it represents the absolute ceiling of current human engineering. A single unit is the size of a public transit bus. Operating one requires a cleanroom facility so large it can dominate an entire industrial park. This visualization shows the base electrical draw of one of these systems measured against the energy capacity of a small municipal town. When the EXE5000 powers up, it consumes an astonishing 1 megawatt of electricity, which raises an obvious question. Why do you need the energy infrastructure of a city to carve microscopic, invisible lines into a piece of silicon? The answer lies in the physics of light. Achieving subatomic precision requires you to apply an overwhelming amount of macro-level brute force. If you move off the factory floor and dive deep into the core of the machine, you arrive in a total vacuum. To print the next generation of semiconductors, engineers need a highly specific tool, extreme ultraviolet light, radiating at exactly 13.5 nanometers. There is a severe physical hurdle here. You cannot harvest 13.5 nanometer light naturally on Earth. It is instantly absorbed by almost any matter it touches, including standard oxygen. Because we can't find this photon in nature, we have to artificially synthesize it from scratch inside that empty vacuum chamber. That megawatt of electricity surging into the system from the grid goes toward fueling the violent sequence required to rip that specific wavelength of light into existence. The process begins with a stream of microscopic molten tin droplets. The machine fires them into the dark chamber at high velocity. First, a laser pulse hits the falling sphere of tin. This impact doesn't destroy the droplet. It acts like a hammer, flattening the tin into a thin disk to maximize its surface area. Microseconds later, a vastly more energetic CO2 laser strikes that flattened disk. The impact vaporizes the tin entirely, creating a highly ionized plasma explosion that finally emits the 13.5 nanometer EUV light. This two-step obliteration, the shaping pulse followed by the main pulse, is repeated tens of thousands of times every single second. The physical timing required to track and hit a falling microscopic droplet twice in a vacuum is roughly equivalent to shooting an arrow from Earth and perfectly piercing an apple sitting on the moon. Vaporizing thousands of drops of tin every second creates a continuous, high-speed shockwave of metallic debris and charged ions radiating outward. If that debris is allowed to drift, it will immediately coat the machine's hyper-polished collector mirrors. The moment those mirrors lose their reflectivity, the entire megawatt system is rendered useless. To prevent the machine from destroying itself, engineers flood the inside of the chamber with a continuous stream of hydrogen buffer gas. This hydrogen flow serves two purposes. Physically, the gas molecules collide with the energetic tin ions, slowing them down. Chemically, the hydrogen reacts with the hydrogen atoms to form stenane, a gas that can be easily pumped out of the vacuum via an exhaust system. Forcing the universe to produce EUV light was only half the engineering equation. The system also had to perfectly manage the chaotic destruction left in that light's wake. The successfully generated, uncontaminated light is collected and bounced off a series of the flattest, most perfect multi-layered mirrors humanity has ever manufactured. This diagram compares the system's target resolution against a strand of human DNA. The EUV light ultimately projects a physical stencil onto a silicon wafer, etching circuitry lines just 8 nanometers wide. That reliable, repeatable transfer of synthetic light onto silicon is the only mechanism currently keeping Moore's law afloat. Every piece of advanced technology currently operating globally routes back through this exact microscopic sequence. It is the definitive bottleneck of the modern economy. Those 8-nanometer lines govern the hardware required to train massive artificial intelligence models, calculate deep space telemetry, and process complex medical data. We reached the point where sculpting the microscopic future of humanity required us to build a ravenous, megawatt-devouring behemoth. It is a paradox of scale, proving exactly what it takes to master the extreme limits of the physical universe.